Okay, this is the video for section 9.2, simplifying radicals. So, in the last section we talked about what radicals were and how you can find a radical when it's a perfect square. So now we're going to look at radicals with all kinds of different numbers under them and how we would write them in their simplest forms. And so we're going to do square roots and cube roots, but a lot of the things that we talk about would go for higher roots, like fourth roots and fifth roots as well. So here's the basic important property here, and that is that if you have two positive numbers multiplied together under the radical, then you can break them up. And so that becomes important because if you have a number, say, like 20, suppose we have the square root of 20, well, I can think of that as different kinds of factors. So 20 is 4 times 5, so that would be the same as square root of 4 times square root of 5, right? Well, we know the square root of 4 because that's a perfect square, so that means that it would be the square root of 4, which is 2 times the square root of 5. And so that's how we will simplify. And you can also do it with fractions. So if you have the square root of a fraction, then you can think of that as the square root of the top over the square root of the bottom. So you can break them up into separate squares. And then we can simplify them like we just did with square root of 20, the top and the bottom, separately. Or if you have two, you can go backwards, right? If you have two separate square roots, you can put them together and then maybe you can simplify that fraction. And we'll look at one of those that you can do that too as well. So just like fractions, you would always write your answer reduced, totally reduced, and in simplest form. The same thing goes for square roots. It's not ever going to be the right answer if it's not in simplest form. Okay, so when we look at square roots, whatever we do to them, just like we did with fractions, in the end, you got to make sure that they are totally in simplest form. So here are the first ones we're going to try. So first of all, the square root of 24. So you want to factor 24 so that it has one number is a perfect square, just like we did with the 20, right? So 24 has a 4 in it, so it's 4 times 6. 6 doesn't have any more perfect squares, and so that would be, we break it up like that, and that would equal 2 square root of 6. Okay, so for something like 24, that works pretty good. Although possibly when you were thinking about 24 and factoring it, maybe you thought to factor it as 3 times 8. And there are no perfect squares there. And then you would have to keep going, right? And we do eventually get that 4, but doing a prime factorization is another method of doing this. And sometimes if you don't see it, it's great to just start by trying to get to the prime factorization. And if along the way you run into some perfect squares, then that's perfectly fine, right? That you can just use it. But thinking about it this way, you might like to think about it sometimes like this, and you can, like I said, you can do a kind of a combination of both. But once you have it prime factorized, if you have the prime factorization, then you're looking for groups of 2, right? Because when I take two numbers, multiply them together, that gives me a perfect square. So I have 2 squared, and it's the square root. So that means that's going to be the square root of 4, which is just a 2. And then there aren't any pairs for this one, right? There aren't 2 2s and there aren't 2 3s left, so they stay under and it becomes a 6. So if you have 2 of the same factor, that can come out, whatever that number is, can come out without the radical, right? Because you're taking the square root of that. And if you don't have 2 of them, then they stay under the radical. All right, so let's look at 72. So when you're factoring 72, so okay, I got this PowerPoint from the publisher of the book, and it's kind of hard to edit it because all the formulas are made in a way I can't edit it. So I've left in here all of these ways they're going to do it, but I'm going to talk along the way about this other way that I showed you, right? And they're actually going to show you some other ways as well. So you may realize that 72 is 36 times 2. And certainly, as you start factoring this and you're thinking, how could I factor 72? You might say, well, 2 goes into it, and you would find out that it's 36, and then, oh, bingo, 36 is a perfect square, so we can stop. And that's what it turns out to be. And that's what I mean by you're kind of doing both. So the square root of 36 then is 6, and square root of 2. Okay, so now here's where they explain how maybe you don't come up with that 36, because I wouldn't have. If I had been trying to factor 72, I would have thought first of 8 times 9. And so 9 is a perfect square, right? So we could go with 8 times 9. But then I would keep going with the 8 because it's not factored all the way down. I keep factoring the 8. So now I have a 9 and a 4 that are perfect squares, and that's fine. That means I have square root of 9 and the square root of 4 and the square root of 2. And square root of 9 is 3, and the square root of 4 is 2, and the square root of 2 will just stay, right? And then I multiply these. So remember, these are all just multiplying together. So in the end, we get 6 square root of 2. So sure, it was easier the bigger the perfect square we found, but certainly not. It's not easier to do it that way if it takes you a long time to find the 36, right? Now, doing the other method that we were talking about, we could have realized this is 3 times 3, and this is 2 times 2 times 2, right? So there's a 3. The 3 comes out because I'd have square root of 3 squared, which is 3. And then I have a 2. There's 2 2's, so the 2 will come out. And this 2 is left over, so it stays under. And that's the other way to get to it. All right, let's look at, let me erase this. The next problem on there was 75 over 4. Okay, so it's a fraction, so I can split it up. And the square root of 4 is easy, because that's just 2. So I can get the bottom done in no time at all. And the top, 75, you're probably going to know it's 25 times 3. And square root of 25 is 5. Square root of 3 over 2. And that's how we would leave it. Okay, so 288. So 288, it's kind of a big number. If you start factoring it, you might realize it's 144. And maybe you recognize that 144 is 12 times 12. So that was our perfect square, so we pulled out the 12. Now, maybe you didn't recognize it like that. So maybe you were looking at 288 and you said 2 and 144, but you didn't notice that that was a perfect square. And so I'd pull out 2 again, and I would get 72. And oh, 72 is 8 times 9. And 8 is 2 times 2 times 2. And 9 is 3 times 3. Right? So I would be looking at, here's 2 2's, so a 2 comes out. Here's another 2 2's, so there's a 2 that comes out. And there's 2 3's, so a 3 comes out. And there's only that 1 2 left over, so it stays under, which is 12 square root of 2. And that would be the numerator, right? And then we would still have that over 3. Okay, well, so the thing is, when you look at this problem, we're not quite done. However it is that you get to 12 square root of 2 over 3, because it was that fraction, we still have to look at the fraction and see if it's reduced, which it's not, right? So we would cancel out a 3 in the 12 over 3, and that's going to be just 4 square root of 2. Now, this is one where we have this this fraction, 288 over 9, and you probably don't know it off the top of your head, but it might be worth a minute to just double check, okay? If we actually check to see 288 divided by 9, well, that goes in evenly, and that is the square root of 32. Okay, so now I'm just trying to reduce the square root of 32. And the square root of 32 is 2 times 16, so that's going to be my 4 root 2. Okay, so the square root and the square, they kind of undo each other, right? So whatever number you have, and you could have a variable, right? If we square it, and then we take the square root of it, we're back where we started. Unless that number is a negative. Okay, so if I said negative 2, and then I square it and take the square root, well, I got to do the parenthesis first, right? I'm working from the inside out. And so that means I take negative 2 squared, that's a 4, and I take the square root, which is positive 2. So you see that they didn't match. So if the inside number is a negative, then it's going to turn out to be the opposite. And that's why we say it with an absolute value. Because if x is positive, then it's great, it turns out to be x. But if x is negative, then it turns out to be x is positive, right? So, most of the problems are going to say that we're going to assume that x is positive or greater than or equal to 0, right? It could be 0. And so if we do that, then we can just write this. We don't have to put the absolute value, okay? So that's why most of your problems are going to say, assume that the variables are all greater than or equal to 0 because of that, okay? So when we have a variable, because we are assuming that all variables are greater than or equal to 0, I don't have to worry about putting absolute values. If it didn't say that, I would have to worry about it. Okay, so when it's a variable, we do it just like always, right? So this is going to be square root of 36. Oh, let me see if it's written in here. Square root of 36 times the square root of x squared. Well, that's just equal to 6 and x. So 6x. Okay, so if it's a variable, we just look at it like it was some number, right? That's doubled. I mean, we got x times x. And so that's going to mean one of the x's comes out. In fact, which was all of the x's, right? Okay, so 75a squared. Let's look at that one. All right, so we got square 75, which is 25 times 3, and a squared. So we're still trying to get perfect squares, and we do it with the number and we do it with the variable. So the number, we got this 25, and that's a pretty easy one. We already did 75 once already. And then the a is squared, because that's all we had was an a squared. And so now we just look at those, right? So square root of 25 is 5, square root of 3 is square root of 3, and square root of a squared is a, right? Now we would write it in a nice order so that we typically write the radical last and the numbers just in front of it, right? Or the variables that are under the radical. Okay, so pause the video and see if you can do this one by yourself. While I plug in my iPad. All right, so we would look at the square at 8. 8's going to be 4 times 2. And then our variables are already in squares, and so we're just including each of them, right? So when we do it, the square root of x squared becomes x, square root of y squared becomes y, and then we write it in a nice order so that the radical is last. Okay, so I feel like they make it harder here than we probably need to be. You notice that anytime we have a square root of some even number, okay, so that's what that means. If m is some integer, any integer, right, then 2 times that is going to be an even number. So anytime we have a square root of an even number, then it just takes it down to that square root of whatever half of that was, right? It takes the exponent in half. That's kind of what the square root does, is it cuts it in half. Just like when we had x squared, right? We had x squared, that became x to the 1, right? So it's cutting that in half. That's what we've been doing all the time. It's cutting the exponent in half. Because remember that if we did, so let's take, for example, if we have the square root of x to the 6th. So according to this, that's going to be x to the 3rd. And it would be absolute value unless we said that x has to be a positive number, right? Now, but think about why this is cut in half. Why did we cut the 6 in half and make it a 3? Well, because if I did x cubed times x cubed, that's going to be x to the 6th, right? So if we square this, that gets us back to x to the 6th. So that's why. If it's an odd number, then when we pull out even pairs of numbers, right, then we have 1 left over. And so that 1 will stay under the radical, whereas the rest of them will come out, right, as we have 2's. So we'll talk about more of these as they come up here. Okay, so the first one here, square root of 16x to the 4th. So we look at the 16, which is already a perfect square, and we look at this x to the 4th. That's going to just be, the square root of 16 is 4, and the square root of x to the 4th is x squared. You know that you could think of this the way I talked about it before, so 16 is going to be 4 times 4, and x, there's 4 of these x's, right? So that's what it's all factored to be. So there's a 4 that comes out. There's an x that comes out. And here's another one that comes out. So that's going to be 4x squared. Instead of trying to remember that rule about cutting it in half, you're thinking about taking them out by 2's, right? Yeah, I thought it was going to... Oops. What happened? How come I... Oh, here we go. I just wanted to erase this so we have room. Okay. Yes. Okay, so this same thing is going to happen here this time. We got the square root of 49, the square root of x squared, which is just x. But the y, we have an odd number of them, right? So I'm going to take them out by 2's. So I have a y squared and a y. That's how I got my y cubed, right? So I take each of those out one by one. Square root of 49 is 7. Square root of x squared is x. Square root of y squared is y. And then that one little y is left under the radical. Okay, so we have 18, a to the 6th, b to the 4th. So pause the video and see if you can simplify this one down yourself. Hopefully you were able to do it. The 18 we could think of as 9 times 2. These are both even exponents, so we can just leave them like that, right? The 9 comes out as a 3. The square root of 9 is 3. The square root of 2 is going to stay square root of 2. The square root of a to the 6th, well, you know, I have 3 sets of a, right, of 2 a's in there. So, or I cut this in half and make it a cubed, however you want to most think of that. And I cut this in half, and I end up with b squared. Okay. Here's the next one. Pause it and see if you can do this. Okay, so the we can split up the fraction, right? And 9 is already a perfect square, and so is 64. So the top a is odd, so that means I can break it up into an even one and a single, right? That would be a to the 15 if I combined them, but I want it to be an even one and a single a. Right, so square root of 9 is 3, and the square root of a to the 14th would be half the exponent, so a to the 7th, and then this a stays under the radical. In the denominator, we have square root of 64 is 8, and this makes half of that exponent, and that's going to be b to the 4th. So, do you see anything there that could possibly be reduced? I don't think so, because 3 doesn't go into 8, and so the top one only has a's and the bottom one only has b's, so that is all the way simplified. So let's see what happens when we have a cubed root. So we would be looking for perfect cubes this time. Okay, so think about the factors of 54 is 27 times 2. Now, sure, we have 27. I would not personally have come up with 27 if I were factoring this. I would have thought of 6 times 9. And 6 is 2 times 3, and 9 is 3 times 3. So there I have my perfect cube. That's my 27, right? But I would have looked at that and said, oh, there's 3 3's. So that means the cubed root of 3 cubed is 3. So the 3 comes out, the 2 stays under. Right? Now the x cubed, because it's the same, there's 3 x's here, and it's a cubed root. So that means it is equal to x. One undoes the other one, right? I'm sure I have that written there. But you saw it. I'll erase it so you can see their answer. And there's the final answer. Okay, let's try this one this time. So pause the video and see if you can do this now. This time we're talking about cubed roots. So we're looking for 3 of something to come out, right? A perfect cube, which is some number multiplied by itself 3 times. So that's why if you factor, you'll find those perfect cubes. Okay, so if you think about 40, it's 8 times 5, and 8 is one of our perfect cubes. If you didn't realize 8 was a perfect cube, you could just keep factoring, and you'd have 2 times 2 times 2. So that means a 2 is going to come out, right? Okay, so I've broken it up into, these are the perfect cubes, and these are the ones that are not perfect cubes. I know it's a perfect cube because this is a multiple of 3, and this is a multiple of 3. So those are perfect cubes. But since I had y to the 4th, I have that one more y that stays under, right? But these are all perfect cubes. So the cubed root of 8 is 2, because it's 2 times 2 times 2, right? And I divide these by 3. I divide the exponent by whatever that index is. Like last time I divided it by 2. Now I'm going to divide it by 3. So I get x squared. And then y cubed, and that cubed root is just a y. So this 3 right here, this is in the index of the radical. It's not an exponent on the y. It almost looks like it is. It's a little bit misleading, but it is. It's inside that little hook on the radical. Okay, here's one more. So pause the video and see if you can do this one. Okay, hopefully you figured out that 125 is a perfect cube. If you started factoring it, and then you would find, so I would, for example, I would know that 5 goes in here, and when I divide it in there, I get that it's 25, and 25 is 5 times 5, so that's how I know 125 is a perfect cube. I have 5 times 5 times 5, so that 5 will come out. Oh, first they're going to combine all the perfect cubes and all the not perfect cubes. So this x to the 8th can be split up as x to the 6th, because 6 is a multiple of 3, times x squared, because I want to get the ones with multiples of 3 so that because they are a perfect cube. And 9 is already a multiple of 3, so it is a perfect cube. So that's why they put all their perfect cubes in the first one and the not perfect cubes in the second one. Right, so that way we can just take the cubed root. So one cubed root of 125 is 5. Like I said, there were 3 5s. And then we divide that exponent by 3 and get x squared. We divide the 9 by 3 and get y cubed. And I still have the cubed root of x squared because that was left. Okay, so sometimes we have a radical expression and it is not just a fraction. So do you see the difference? It is not just a fraction because there is this plus sign here and this minus sign over here, right? And no, I know you're tempted, but you cannot take this 3 and this 3 and cancel them out. It doesn't work that way. So you can only cancel when the reason we cancel is because you're multiplying by 1. If you have 3 over 3 and you multiply it, that's like a 1. So that's multiplying by 1, which doesn't change the answer, right? But this is not multiplied. This 3 is not multiplied. It's added. And so I can't take out the 3 over 3 when it's added. It has to be in a multiplication setting. So the first thing we're going to do is we're going to simplify that radical and see if we can make it simpler, right? So just looking at the radical, we would take 18 and make it 9 times 2, because 9 is a perfect square, and square root of 9 is 3. So now I have 3's in each one of them. So I can factor this and make it a multiply. And my goal in factoring is so that I can reduce, right? Because once I factor, then I can reduce. And I get the 1 plus the square root of 2. So because this, if you're ever going to simplify by reducing, it has to be in both of them so that you could factor it out and cancel it. You can never cancel when there's an add or subtract. But there is another way to think about this. You can actually, so you can start by breaking it up. I mean, in the end, we're doing a lot of the same work. But you can actually split this up into 2 parts. And I actually could have done that. I could have done this step up here right after this, right? I could have split it up first. And I would have known, see, I could have had 3 over 3 plus the square root of 18 over 3. And I would have known that was a 1. But I still would have had to simplify that square root of 18. So no matter what, you don't get out of that. I would still simplify the square root of 18 and make it 3 square root of 2, in which case I could still simplify. Okay. Did I go too fast and you see that it's the same answer, right? Okay, so here's another one. So let's just take this a little bit at a time. So you start by simplifying that radical. Just get that far and see if you can get it down to some nicer radical that we can work with. Okay, hopefully you found that the radical simplifies 20 is 4 times 5. And the a squared has an even exponent, right? So the 2 from the square root of 4 comes out. The a from the a squared comes out. The 5 stays under. Okay? So now I have something that I could factor. I could pull a 2 out of both of them, and then I could cancel the 2's. And that would be my answer. So hopefully that's where you're headed. Or if you wanted to do it the other method, you still have to simplify the radical, but then you can break it up. You break it up into 8 over 2 and 2a root 5 over 2. And simplify each one of them, and you get 4 minus a squared 5 still. Okay, here's some practice problems. Pause the video and work out these practice problems, and come back and I'll show you the answers. And if you have any questions, be glad to talk about it in class next time. Right, here are the answers. Hope it makes sense. I'll see you in class.